when we want a higher frame rate, right? And when do we want a higher frame rate? When we're tracking movement of a moving structure such as a heart. Okay, now, when is it okay to have multiple pulses per scan line to help our image look better? When something is stationary, right? So we don't have to track the movement. We don't have to show that the structure is moving at a certain velocity, right? Okay, so 3 factors determine the number of pulses needed to create each image. Okay, the number of pulses per scan line, the sector size. What's the sector?
The beam.
Like the pie?
So the sector is the image that we see on the screen. So we don't see the whole ultrasound image on the whole screen, right? It's kind of like that blunted pie shape, right? And then there's black on each side.
Yeah.
Okay, so we can make that ultrasound image, we can make that sector smaller, or we can make it bigger. Okay, so we can make it to where it's a smaller sector size. Okay, so what would be the benefit of having a smaller sector size?
A higher resolution.
What type of resolution?
Uh-huh.
No.
Elevation? I don't know.
Temporal resolution, okay, temporal resolution. Because we're making, so instead of having to use, let's say, 100 scan lines to make our normal image, we're making it smaller so it has less scan lines. So instead of 100, we have 50. So we improved the temporal resolution by 50%, okay, because we got rid of some scan lines. Okay, and the lines per angle of sector. Okay, so on a curvilinear transducer, we have that whole array to work with, right? And each of those crystals sends out a scan line. Okay, so we could, again, we could make our image smaller, that reduces the lines per angle, or we could make our image bigger and increase the lines per angle of sector. So if we have, so it's kind of, so our image is like this, right? Okay, that's what the ultrasound image kind of looks like. Oh, sorry. Like that, right? Okay, so each of these has an angle. Okay, so if we're imaging our liver, right? If we're imaging our liver, what do you think the liver is going to look like with that type of line density, of that many lines? Huh? Okay, so let's say the line density is like this. Okay. Which one's gonna look more accurate?
The right one?
This one?
Yes.
Yes. This one's gonna look more accurate because there's more scan lines, right? It's going through each section of the liver. This one, we can still see the liver, but it's gonna look kind of blurry, right? That's because it's missing information in between these lines.
Okay, the temporal resolution.
Yeah, so this is temporal resolution at this point. So which one of these has a better temporal resolution?
All right.
So A and B.
B.
A has better temporal resolution because there's less scan lines, right? Okay, but which image looks better? B, because it has more scan lines. Okay, so in which one of these would you use to scan the liver?
B.
And then which one would you use to scan the heart? A, right? Because we need improved temporal resolution, and the heart isn't as big as the liver, right? Okay. Does that make sense?
Would you explain the lines again? Or B?
Yeah.
It would be better for the liver because of how many scan lines are in there.
Exactly, because of how many scans there are. So in between these lines, there's missing information. Okay, so that translates to a blurry image. Okay, now if we have the scan lines to cover the whole liver, then we get the whole picture of the liver accurately. Okay, remember, we're trying to improve resolutions. We're trying to make it look more accurate. Okay, so we do get a better image here, but our temporal resolution goes down. Okay, but at this point, we don't care about that because our liver doesn't move, right? Okay, now, if we were imaging the heart would look beautiful, right? But the temporal resolution would go down, so the valves would look like if they were kind of like, they were skipping or like mumbling, right? So then we would have to decrease our scan lines to increase the temporal resolution to show the accurate movement of those valves.
I have a question.
Yes.
Is this, the line density, is this something you can physically adjust? Like,
Yes. that's
yeah,
something
right?
that you
There's
can
a button
do.
for that, right?
Yes. There's a button for line density. And it's either called line density,
Or
it's a
linear.
knob that you can increase or decrease, or also persistence. Okay, so the three factors that determine the number of pulses needed to create an image. Number of pulses per scan line. Okay, so if we have a single focus, how many pulses do you think we have?
One?
One. Do we have multiple focus or foci?
Multiple? A lot?
So the number of pulses would be the number of focal points we have. Okay, so if we have 3 focal points, we're gonna have 3 pulses per scan length. Does that make sense?
And what did you say they were called? Focal?
Focal points, yes. Okay, so let's do some math. All right, so let's say that we have a sector, right? That sector has a field of view of 90 degrees. And there's 1 scan line per degree. How many pulses? With 1 focus, there's 90, right? Okay. So there's 1 scan line per angle, which is 90. Okay, what if we put 2 focal points? How many pulses would we have?
45.
No, 180. 90 times 2 is 180. Okay, now, if we went from 90 to 45 degrees with 2 pulses, how many pulses will we have? Which is 90.
Does it do 90
Are you guys still?
line
90 pulses.
pulses?
Yes, there's 45 lines, but there's 2 pulses per line. So 45 times 2 is 90. Okay, so we went from 90 degrees and we reduced it to 45, but then we added 2 pulses instead of 1.
So the equation is like lines of pulses times
Focal points.
focal points?
Yeah.
So what would the question be, like, what would you ask us?
Okay, so I would say this image has a field of view of 90 degrees. How many pulses would it take if there's 1 scan line per degree
90?
and 1 focus?
90.
90. Okay, then I would ask you, if we reduce that to 45, what would it be? Okay. So there's 45 lines and 1 pulse per line. Okay, but just know that I'm gonna add in a focal points. Huh?
Why?
Because you need to know how to do the math. Use your head. It's not just there to hold up your hair. Okay, multifocus. So an individual sound beam has 1 focus. With multifocusing, more pulses are transmitted down each scan line. The number of pulses needed to create an image increases. Okay, so here, how many focal points are there? 1. Okay, but you see this little dot right here? Those are pulses. Okay, so all these arrows are focal points. So how many focal points do we have? 5. Okay, so how many scan lines do we have? 2. 1, 2, 3,
Is
4,
the
5,
outer
6, 7, 8,
sides?
9.
That counts as a line? Is that just the one that's it?
I would say yes.
Okay.
So 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 times 5 is what? 45. Okay, so this one took 9 pulses to create the image, This one took 45 pulses to create the image.
Oh,
Okay.
that makes sense.
So, which one has better temporal resolution?
Left,
Left, because it has less pulses.
yes.
Which one will make a better image?
Right.
Right, because it has more scan lines, it has more pulses. So if we add more pulses, what are we doing to the sound beam?
Shortening it.
No, I'm shortening it,
Narrowing?
making it narrow, okay? It's more intense, but it's more narrow. At what resolution? What resolution? Lateral resolution. Okay, so our lateral resolution is being improved because the diameter of the sound beam is smaller across a bigger area.
Mhm.
Okay, so single focus, 1 pulse per scan line. We have a shorter T frame, which means that we have a higher frame rate, which means we have better temporal resolution, but we have poorer lateral resolution because our beam is a bigger diameter at a longer distance. Okay, now when we have multifocus, we have multiple pulses per scan line, longer T frame, which means our frame rate decreases, which means our temporal resolution decreases, but we have improved lateral resolution. Okay, so more scan lines, more pulses, better lateral resolution, but poor temporal resolution. Okay, less pulses means better temporal resolution, but we have poorer lateral resolution. Okay, does that make sense to everyone? Yes?
Yes.
Okay, so here we have a single focus versus multi-focus. Okay, so as you can see here, how many pulses do we have? We have 3 pulses per scan line, right? And then we have an array of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21? 21, right? Okay, so, but there's 3 pulses per scan line, so how many pulses in total? 63. And this one has how many? 21. So which one has a better temporal resolution? The top one, right? But which one has better lateral resolution? The bottom. Okay, so we could say that our temporal resolution was really good on this, but it doesn't help us out with anything because we can't see the hepatic veins. But we increase the focal points. We have 3 focal points now. Now we see the hepatic veins. Okay, so what is adding multiple focal points do?
Improves the temporal resolution.
No,
Improves lateral?
it improves the lateral resolution. Okay, by doing what?
Sending out more
Narrowing
pulses.
the beam width.
It narrows a beam width over a longer distance. Okay, so maybe we could say here that our focal point was right here, right? Because we can see this pretty clear. Okay, past that, we can't see anything. So this tech added a focal point here, a focal point here, and a focal point here. So now we see the entire liver. Okay, does that make sense? Yes, sure. Paul?
I think I get it.
The only thing is the heart. I know why.
Okay, so we're not worried too much about lateral resolution so much for the heart, okay, because there's multiple factors. Okay, so where is your heart in your body?
Your left side and your chest.
Point to upper chest. Here, right? So if I were to take this thing and stab myself with it, would I be able to hit my heart?
Yeah, most likely.
Yeah, most likely, right? So we can say that the heart is very superficial. Okay, so there's less distance it needs to travel, which means what?
Better.
Shorter pulses?
Huh?
Shorter pulses?
Shorter pulses, right? Shorter pulses, which means an increase in frequency, which means that the temporal resolution is already gonna be good, okay? Because it doesn't have to go through that much depth. Okay, secondly, the heart is very fast, right? It beats pretty fast, hundreds of beats per minute. Okay, so we need to be able to identify if those valves are working efficiently, if the walls are contracting enough efficiently and accurately, most importantly accurately. So we have that because we have improved temporal resolution. Okay, so that's why we don't need to make sure that it's looking perfect. We just need to be able to see the valves, and then if we put color on it, we just need to see the blood moving from ventricle to atrium and from side to side, okay? So that's why it's not that important to have improved lateral resolution with the heart. Okay, now we have our sector sites. It's also called a field of view, or FOV. Field of view, FOV, same thing. Okay, so when the sonographer expands the field of view, more pulses are required to create an image. Okay, so here we have a smaller sector size, right? So this one's 90 and this one's 45. Which one has a better temporal resolution? 45.
Yeah.
Okay. So when is this beneficial for us to use? What do you guys think?
The heart.
Okay, so what's this right here? Circle, yes, very good, it's a circle. It's a circle with some black and gray stuff. Okay, so this is a transverse view of a fetus.
Cranial?
Okay, so these are the ribs, this is the heart, and this is edge shadowing by the ribs. Okay, so look at the difference between how the heart looks here and the heart looks here. Do you guys see the difference? We could actually see the valves within the heart. We could see the hyper-echoic septums of the heart, right? And this one, we could kind of see the outline of the heart, but we really can't see anything, right?
No.
So what did this sonographer do?
She used the sector size small.
Yes. What did this she?
He, them, it.
Okay, so this sonographer changed the sector size, right? Okay, so the sector size changed and it made our image look more defined.
Yeah.
Okay, so look at the space in between the lines, between this one and this one.
The narrower.
Yeah, there's a lot less space on the smaller field of view, right? So if we have a shorter diameter between, what happens?
Temporal resolution.
Oh, lateral resolution. Remember, if it's becoming shorter, it's going, or like skinnier, it's gonna be lateral resolution. Okay, so the lateral resolution improved and the temporal resolution improved
Yeah.
because there's less scan lines. Okay, so if the ultrasound system creates a 30-degree sector with one transmit line per degree of sector, how many pulses are made?
30.
30.
30. Okay, and if we reduce that sector size to 15 degrees, how many pulses will we have? 15. Okay, so that means that our temporal resolution
Increase.
was improved.
Improvement.
Yes? You guys follow me?
Yes.
Yeah. Okay, so line density. What do you think line density is?
The space between the sides.
Okay.
It's right
You
there.
read that. So yes, it's a space between each line. Okay, so if we have more line density, we have less space between lines. Is that good or bad?
Bad.
It depends on what we're imaging, right? It's good because what is having less space between soundings are being with narrows, which improves
Lateral.
lateral resolution, okay? But that means that we have more scan lines, so what gets degraded?
The temporal.
The temporal resolution, okay? So when is this beneficial? For what type of imaging?
For deep abdominal.
Abdominal, right? For pretty much anything where we don't have to worry about movement. Okay, now if we have a low density scan line where there's less scan lines, okay, what improved? The temporal resolution, but what degraded?
Lateral.
Lateral resolution, and when is this okay?
The heart, moving structures.
Yes, the heart, for cardiac imaging, okay, for echo. Okay, so the lines may be spaced far apart, which means we have low line density, or closely packed, which means high density. Okay, have you guys ever been fishing?
Yes.
Okay, so, when I go fishing, I have two different types of nets, depending on the type of bait that I wanna use. I have nets that have a small, space, and that's because I wanna catch whatever I can catch. And then I have another net that has a big space in between, and that's just to catch bigger fish. Okay, so this kinda works it the same way. Okay, so if we have a high light density, we're gonna catch all the echoes. And if we have a low light density, we're gonna be catching only the strong echoes. Okay, which means that our overall image resolution is gonna be bad, but our temporal resolution is gonna be good. Okay, so now if the ultrasound system creates a 90-degree sector with a line every 2 degrees, how many pulses are there?
45.
45.
45. It's every 2 degrees. Okay, so again, don't rush. Okay, so if an ultrasound system creates a sector of 90 degrees with a line every 2 degrees, how many pulses are there?
45.
It's 45, right? Because it's every other line. So what's 90 divided by 2?
45.
45. Okay, now how many pulses are made?
Sorry.
90.
I had a voicemail, I shouldn't read it.
Okay, so how many pulses are made if there are lines at every degree?
90.
90. Right? Does everybody understand that?
Yes.
Okay, now, if an ultrasound system creates a sector at 90 degrees with a line every 2 degrees and there's 2 pulses per scan line, how many pulses did it make?
40.
90. Okay, because it's 45, it's every other degree, but I added 2 pulses instead of 1.
So it's
So 45 times 2 is 90.
Mm.
Okay, so whenever I have a 90-degree sector with a line every 2 degrees and I reduce the field of view from 90 to 45, how many lines do I have? Or how many pulses do I have?
22.5.
22.5?
No.
22.5 times 2 is what?
40.
45? Yeah, but do we ever have half a degree?
No.
No. But I'm gonna ask you that just to mess with you. I'm just kidding, gold, I'm not, I promise.
So if you ask us that, do we round it?
No, I'm not gonna ask you that. Okay, small gaps improve image accuracy and quality, but they degrade temporal resolution. Okay, again, it's a give and take, and it depends on what type of imaging you're doing at that time. Okay, so low light density, we have widely spaced lines, fewer pulses per frame, which means that we have a shorter T frame, but we have a higher frame rate and a higher temporal resolution, but we have poor spatial resolution. And what resolution contributes to this poor resolution? Lateral resolution. Okay, now we have high latency. Tightly spaced lines, more pulses per frame, which means we have a longer T frame, which means our frame rate is lowered, which means our temporal resolution is lowered, but we have excellent spatial resolution. Okay, so depending on the type of imaging we are doing, we need to adjust our light density to optimize the image. Okay, does that make sense to everybody?
And you said so there was a button on the machine that allows us to control the line density?
Yes. Let me see if the actually some has it.